Okay, I'm going to pick up where we left off yesterday. Theorem 4, the sandwich theorem. Sounds like my kind of theorem. Suppose that g of x is less than or equal to f of x is less than or equal to h of x for all x in some open interval containing c, except possibly at itself. I crack myself up. Suppose also that the limit as x approaches g of x, or the limit of g of x as x approaches, it doesn't even matter what number, is equal to the limit of h of x, which is equal to L. So I have some limit that occurs, and it's the limit of g of x and the limit of h of x equals the same thing. So basically, whenever I'm looking at this, that tells me that the limit of f of x equals L. So I'm going to describe it graphically to you, just simply so you can see what we're talking about here. So let's say I have some value g of x, okay? And we'll say that g of x comes down and curves like this. So it is, as I'm approaching 0, it's approaching this point here. We'll even say that that's 1, right? So that's g of x. Then let's say I have f of x, which starts out higher than that, but it comes down and approaches the same point and goes down like that. All right? And then I'll say I have, so let me label these. I have g of x here. So g of x, if you look at it, is always below h of x, or f of x that I just drew. I messed up when I drew f of x. So now we're going to draw it again. I need my f of x to be above Okay, so it's coming down like this. G of x is below f of x, which is in blue. And then f of x is below h of x all the time. So this green line needs to be above the blue. A little hard to draw it, but you get the point. Green is above blue, blue is above red. So the sandwich theorem says that if g of x approaches, say, 1 when x is 0, so if I'm finding the limit of g of x as x approaches 0, and that is 1, and the limit is as x approaches 0 of h of x is also 1, then what's in between them has to be 1 as well. So because f of x is always going to be between h of x and g of x, if the limit is 1, or if the limit is L for g of x, and the limit is L for h of x, then the limit has to be L for f of x. This is also called the squeeze theorem. It's called the squeeze theorem because both of these are approaching the same thing. So I have a red approaching some point, and my green is approaching some point, and I know my blue can't get outside of the red and green. So if red is going to some point and green is going to the same point, then the blue also has to be going to that same point. Guess that would have been an easier way to draw it from the very beginning. So it's being squeezed in, or it's like the middle part of a sandwich. I mean, I'm not going to have my bologna outside the bread. Not that I really eat bologna, but the bologna is going to be in between the two slices of bread. It's not going to be on the outside. The blue, or f of x, is being sandwiched between g of x and h of x. Or it's being squeezed. H is squeezing down, g is squeezing up, and f of x is in the middle. It's like when you are getting into a car. You know, you have to get in the middle seat in the back, and the two people that get on the outside of you, say like two of me, if I'm on the right and I'm on the left, you're going to be squeezed into the middle there. So you can't fall out of the car door because you're being squeezed inside of it. That's a lot of different ways to illustrate the same thing. Okay, so let's look at it mathematically. Here I have 1 minus x squared over 4 is less than or equal to u of x is less than or equal to 1 plus x squared over 2. It says find the limit as x approaches 0 of u of x, no matter how complicated u is. So if I'm looking at the limit as x approaches 0 of 1 minus x squared over 4, then I can first try to plug 0 in and see if it's going to mess me up. If I plug 0 in, that just gives me 0 here. So that gives me 1 minus 0, which is 1. If I look at this function over here, I have the limit as x approaches 0 of 1 plus x squared over 2. If I plug a 0 in for x, that gives me 0 squared, which is 0, divided by 2, still 0. 1 plus 0 is 1. So I know that my limit for the lower function is 1, and my limit for the higher function is 1, and u of x is always in between those two. So since it's always in between, then the limit as x approaches 0 of u of x equals 1. U of x is always between this one and this one, and those both go to 1, so u of x also goes to 1. If you were here, you could let me know whether you understand that or not. Probably why we should come to class. Oh well. Theorem 5. If f of x is less than or equal to g of x for all x in some open interval containing c, except possibly at x equals c itself, and the limits of f and g both exist as x approaches c, then the limit of f of x, limit as x approaches c of f of x, is less than or equal to the limit as x approaches c of g of x. In other words, if I have two functions and one is always bigger than the other, then the limit of the smaller one has to be either smaller than or equal to the limit of the bigger one. And that only makes sense to me. If it's always smaller, if f of x is always smaller than g of x, then the limit, or equal to g of x, then the limit always has to be smaller than or equal to g of x. Done. Okay, that's really the end of this section. So I've assigned you some homework for tonight. I am going to go over some of the homeworks that we haven't gone over yet from previous classes. So let's get into them. So let's look at number 3. This is from 2.1 day 4. So if we look at number 3, it says the limit as x approaches 0 of f of x exists. So I need to be approaching 0. So as my x is getting closer to 0, y gets closer to 0 from the left side. As my x approaches 0 from the right, it's like I'm driving up this road to get to a certain point. So as it approaches from the right, it also goes to 0. So this would be true. The second one, the limit as x approaches 0 of f of x is 0. That's true because y equals 0 as x gets closer to 0. So that is also true. The limit as x approaches 0 of f of x equals 1. This is not true. This is false. And it's because we're not looking at the exact point where x equals 0. We're looking as it gets closer to 0. Now, if I asked you f of 0, so what is the exact point of y when x equals 0? It would be 1 because this point is here. But we're looking at the limits, which is just as it gets closer and closer from the left and right, what is happening to our values of y as it gets closer and closer. Part D, the limit as x approaches 1 equals 1. So if I'm going to x approaching 1, what happens to my y here? This one goes to -1. If I approach from the right, it goes to 0. So it's definitely not 1. If I come from the right, the limit as x approaches 1 of f of x is 0. But if I come from the left, it's -1. So that's false. And the limit of f of x exists at every point x naught in this interval. Well, if I'm doing from -1 to 1, that would be true, because it's always going to some point here. Like if I pick a random x and say, as it approaches x from this direction, and from that direction, do they go to the same point? Yeah, they go to this point in the center. And this is not including 1 or -1, so this would be true. Number 4, the limit as x approaches 2 of f of x does not exist. So as x is approaching 2, what's y approaching? It looks like my y gets closer and closer to 1 from the left and to 1 from the right. So that is false. The limit of f of x equals 2. Part B is, there's something wrong with that. Wouldn't have been able to do that. I don't know if it copied wrong or what, but there has to be some x. It's got to be approaching some point. Like the limit is x, f of x. Limit is x approaches 0 of f of x. That's just missing something. Part C, the limit is x approaches 1 of f of x does not exist. This is true. If I'm coming from the left, it looks like it's going down towards -2. If I come from the right, it goes to 0. Those are two different points, so it does not exist. Limit is x approaches x naught of f of x exists at every point x naught in -1 to 1. So I'm looking from this interval from -1 to 1, do they all approach some point from the left and right? And that's not including 1, so I can't go higher than 1 to check this. So this would be true, because no matter what point I choose, I can choose here. If I go to the left from that point, it goes to that point. And if I go to the right, it goes to that y value. So it's the same y value from both directions for every point inside of here. Part E, does it exist at every point from 1 to 3? And this would also be yes. Even though at 2, at f of 2, it's equal to 0, the limit as x approaches 2 is 1. because it's going up towards 1 as x goes to 2. My y goes towards 1. Number 9. The limit as x approaches 1 of f of x equals 5. Must f be defined at x equals 1? If it is, must f of 1 equal 5? The answer to this is no. It doesn't have to be defined at x equals 1. And it's kind of like this example up here. Just because it's defined, or just because we have a limit going to 5, doesn't mean that we have to have a point there. And if I wanted to describe this, I could draw my own example. So let's say we're out here at x equals 1, and this is 5. I can draw a line and have an open circle on that line, and then have the line keep going. So that at this point, there is no value, but the limit does exist. It says, can we conclude anything about the values of f at x equals 1? No. We have no idea what that actual value would be. We know that as you get close to 1, our y value is 5, or our limit is 5. But we don't know what that actual value would be. Number 10. If f of 1 equals 5, must the limit exist? This is kind of the opposite. This is saying I have a certain point here that I know does exist. Right? So this point right here does exist, and it's at x equals 1 and y equals 5. But then I could have these approaching anywhere. So we can't say anything about the limit just because we know that it exists at 5. Numbers 13 and 14, you really just needed to plug those into Desmos. When you plug those into Desmos, you'll be able to find what the values are, zoom in, and trace the line. So those two were easy, and I think I showed you multiple examples on how to do those ones. Okay. Now if we look at our next homework assignment, which is the first homework assignment from this section, in exercises 1 through 6, I could just plug my value in. So for number 1, 2 times -7 is -14, plus 5 is -9. Plug 12 in. -3 times 12 gives me -36. 10 minus 36 is -26. Number 3, plug 2 in. 2 squared is 4, and it becomes negative, so it's -4 plus 10 minus 2. -4 plus 10 is 6, minus 2 is 4. Number 4, plug -2 in. Gives me -8 minus 2 times 4, so that's -8, minus 8 plus 8. Those two are going to cancel each other out. I'm left with -16. Number 5, plug a 6 in. 8 times 6 minus 5 times 6 minus 7. 6 minus 5 is 1. 6 minus 7 is -1. I get -8. Number 6, plug 2/3 in. 3 times 2/3 is 2. And then this would give me 2 times 2/3, which is 4/3, minus 1. That gives me 1/3 times 2, which is 2/3. So 1 through 6 should have been very easy for you. No reason to not get this. All right, number 19 is where it starts to get a little harder. If I plug a 5 into the denominator, that's the first thing I'm going to try. 5 squared is 25. 25 minus 25 gives me 0 in the denominator. That's a problem. So next I'm going to look to factor my bottom out. So this limit is x approaches 5. And if I factor that bottom out, that's the difference of 2 squares. So x times x gives me x squared. And 5 times negative 5 gives me negative 25. Now I can cancel my x minus 5s out. I'm left with the limit as x approaches 5 of 1 over x plus 5. Plug my 5 in. That's 1/10. Number 20. If I plug a negative 3 in, that's 9 minus 12, which is negative 3, plus 3. That gives me a 0 in the denominator. So I need to factor my bottom out. That's x plus 3 over, see if I can factor these. Well, multiplies to give me 3 and adds to 4. 3 plus 1. Now my x plus 3's will cancel. I'm left with the limit is x approaches negative 3 of 1 over x plus 1. Plug the negative 3 in now. It gives me 1 over negative 2, which is negative 1/2. Number 21. See if I plug in negative 5 in, it gives me a 0 in the denominator. Factor the top out. What multiplies to give me negative 10 and adds to 3? That would be positive 5, negative 2. X plus 5's will cancel. I'm left with the limit is x approaches negative 5 of x minus 2. Plug the negative 5 in. That gives you negative 7. Number 22. Kind of the same thing. What multiplies to give me, we'll first plug the 2 in. I get 0 on the bottom. So now I have to factor the top out. What multiplies to give me 10 and adds together to give me negative 7. That would be negative 5 and negative 2. X minus 2's cancel. The limit as x approaches 2 of x minus 5. 2 minus 5 is negative 3. Number 23. You can see it's the same pattern. 1 squared is 1. 1 minus 1 is 0. Factor out my top. It gives me t and t. And then what multiplies to give me negative 2 and adds to 1. That would be a plus 2 and a minus 1. In my denominator, I can factor t squared minus 1 out. That's a difference of 2 squares. What multiplies to give me negative 1 and adds to 0. That would be t plus 1, t minus 1. T minus 1's cancel. I'm left with the limit is t approaches 1. Plug the 1 in. 1 plus 2 is 3. 1 plus 1 is 2. My limit is 3/2. And last one. I'm going to factor my top out. What multiplies to give me t squared plus 3t plus 2. It's going to be a t and a t to get the t squared. What multiplies to 2 and adds to 3. That would be 2 and 1. In the denominator, I guess I should have checked that first. Negative 1 squared is 1. minus a negative 1 is 1, so that would be 1 plus 1, which is 2. Minus 2 gives me 0. Had a feeling it wasn't going to work. I think I did it yesterday. What multiplies to give me negative 2 and adds to negative 1? That's going to be t minus 2 and t plus 1. Those plus 1's cancel. Looking at the limit as t approaches negative 1. Negative 1 plus 2 is 1. Negative 1 minus 2 is negative 3. Negative 1/3 is our answer. All right, well, you have your assignment posted. Let me know if there's any questions. You should probably start coming to class at some point, especially now that we're coming back.